in this first session, let's talk a little bit about what we are going to cover in this set of talks. This set of talks is about astrostatistics, and in particular what is astrostatistics essentially, okay, or what I think is astrostatistics. Let me be a little more cautious here. In this first session, which is really short, let us just look at what we can expect from these sessions. So, here is an outline of these sessions. This particular session, let me call it the prologue. I am going to talk a little bit about this statistical computing environment called R, which is being used by many people around the world to do statistical computing. So, essentially it will involve a quick and dirty introduction to R. This is not an extensive introduction, this is not a course on R, but just what I think is bare essential to be able to get into R, some bare basic familiarity with R, and something that should help, I hope, to learn R on your own if you decide to do it. So, couple of sessions are devoted to R. We will then use R to okay. One example of usage of R is one theme that I use in my probability classes often, that you can use a computing platform like R, it does not have to be R, but something like R, to explore concepts in probability and statistics, and oftentimes this computational exploratory approach can give you interesting insights. This is of course not a substitute for formal mathematical analysis and proofs, but nevertheless the essential insights can be obtained through computational exploration. The third part here is relates to data, and specifically why should one try to understand the data as best as one can before getting into data analysis. This particular session talks about tries to make a compelling case of trying to understand the data before delving into formal statistical analysis, and in particular it tries to bring out the importance of visualizing the data as best as one can, given the structure and complexity of the data. One of course has to devise clever visualization strategies, but exploring, visualizing, and ultimately understanding the data as best as one can before getting into formal statistical analysis is something that one why it is necessary. That is what I will be talking about that. In the next sessions, I will be presenting 3 astrostatistics case studies, which are essentially data driven explorations into 3 different astrophysical phenomena and data sets. And in particular, what I hope to bring out is this fact that you have a science question or a astrophysics, astronomy question to be answered. Now, given the nature of the question and given the available data and the structure and complexity of the data, one needs to make a decision through exploration, through through exploration and through whatever insights you might have on the methodology side. You need to come up with a statistical methodology that can be used to answer those questions, and then in the end statistical methods oftentimes boil down to computing. So, the computational aspect is not really ignored, but it is I am not emphasizing that part. So, essentially you have a scientific question to be answered, and then based on the question you choose your, based on the question and the available data you choose your method. That is something that I hope comes out of these 3. And finally, we will just summarize what we did in these sessions. I have made a few assumptions here, something I hope is bare minimum, but okay. So, I am assuming that you as the audience, you as the viewer of this series of talks, you have some familiarity with computing. It could be any computer programming language, it does not matter, so long as you have some familiarity about how computing is done, some exposure to computing, some exposure to some programming language or a scripting language like Python, R, Julia, MATLAB, whatnot, IDL, so on and so forth, anything is fine. I am also assuming that you have some exposure to notions of probability and statistics. It does not have to be very elaborate. Please do not get disheartened or discouraged because I am assuming something. I am assuming it at a minimal level. I do explain certain things both on the probability and statistics side and occasionally on computing side at a very high level, which I hope will be useful to get the bigger picture. If you have to go deeper in the details, you will of course have to get more deeper into these individual domains, but the purpose here is to give an overview of astrostatistics. So, I am keeping it at a sufficiently high level. You can find lots of resources if you have to go deeper into computing or into statistical inference. So, I am not doing that here. And even if you do not have this background, I am just hoping that these talks will give you a broad high level overview of what astrostatistics is, and that is where okay. What I have not done in this particular session is I have not really defined what astrostatistics is. We will address this question in the very last session, because by that time you would have got an overview of astrostatistics in a hands on kind of manner. So, we will not define statistics here, but then I am hoping that you will get a broad picture of astrostatistics anyways, and we will then take it up in the last session, the task of defining astrostatistics in some sort of loose way. Okay. Okay, in this session we will be talking a little bit about this statistical computing environment called R, which can be quite useful for quick and dirty, that is the long form for Q and D that I have put in the title. It can be quite useful for quick and dirty explorations of variety of things, and for prototyping algorithms and so on and so forth. So, we will quickly go through a really quick introduction on R. This is not a detailed introduction, but hopefully if you ever need to learn R. Okay. Okay, what is R? It is a open source programming platform which is rich in statistical computing primitives. The websites are listed here. It is an open source thing which has been around for 20 plus years. So, it has a very large user base and developer base. People have been contributing packages and so on. So, whatever you need to some computation you need to do, it very likely it will be available in the R packages list. R source binaries and packages are available on the CRAN website. There is also very large amount of community support here for R, which is also another thing that makes it easier to use, easier to learn and so on. I remember long ago, 15 years ago, when this single letter name R used to be very hard to search using Google or any other search engine, but these days search engines also have become smarter, and the R presence on the web also has increased quite a bit. So, it is much easier to find information on the web also. So, these are the two primary websites. Apart from these, there are huge amounts of tutorials, books, video lectures, everything available on R. So, it is quite easy to learn R. We will just go through the really very basic introduction. Yeah, as I said, the R project home and CRAN are these things. One of the books I recommend for beginners is this e-book by Navarro, and the website is mentioned here. The PDF is available at the book is also published. So, feel free to use this book or any other resources that you might find on the web. What we will do now is just quickly go through the really basics of R. For this, I will need to switch over to the R console. The outline of what I am going to do is right here. We will talk about the I basically use the command line interpreter, but GUI environments for R are also available, but the primary mode of using R is still the command line. RStudio is one such GUI which has been around for quite some time, and it's popular amongst a large community of R users. Jupyter notebooks are also quite handy. We'll talk about how to invoke and exit R. This is basically the outline, and we'll go through these things one by one. When you start R, currently R is being run on a Windows system. When you start R, what it shows is a command line interpreter interface, which starts with a message like this thing, and there is the interpreter prompt sitting right here. So, this is how it looks. Now, the Windows version of R comes with its own GUI menu driven kind of thing. So, I will not get into that part. We will just use the command line interface extensively. Okay, this is the command line prompt for R. This is where it is waiting for you to enter commands. So, starting R on a Windows system is just clicking an icon on the desktop, or on a Linux system, you if it is installed in a system wide fashion, then most probably it will be available on the path. So, you need to start a terminal and invoke R from the terminal. In any case, the command line interpreter interface looks something like this thing. One of the things which is very counterintuitive about R is how to quit R. So, I think they have made it a part of the standard message here. You can quit R using Q parenthesis parenthesis. This used to be quite counterintuitive long ago, but these days, at least in the Linux version, Control D also works, like with many other Linux tools. But this is the standard way of quitting R. So, this is one of the things I wanted to point out. You can use like all command line interpreted in environments, you could use R as a quick and dirty calculator. So, for example, this works as you expect it to be. So, this also tells you that numbers are represented as standard numbers. Standard arithmetic operators like multiplication here, they are very much similar to the similar operators in other programming languages. So, another thing I would like to point out is how to find information in R. So, the standard workhorse for all information within the R interpreter is this function called help. So, for example, if you ask for help about the star operator, it will this is how it does it on a Windows system, that it opens a browser window and shows the help on that. Typical help pages have this structure where there is a one line description here, followed by the usage patterns. It will also talk about the arguments for that particular operator or function. The next part gives you details about what this function or this entity does in R, what value it returns. There might be additional information about what this function does. It also gives some sort of references. Oftentimes, the most useful part is the examples at the end of the help page, because they actually give you usage patterns and examples which you can directly copy paste if you have to. Sometimes examples will contain a piece of code which you can use directly in your own work. So, this examples section is something that people tend to use very often, very frequently, once they get familiar with once they have the basic familiarity about R. So, this is how the help system works. I will just minimize this window. I am back into the R interpreter environment. As I said, okay, another useful thing about the R command line interpreter is with the cursor keys up and down arrow keys you can fetch the previous commands. This saves your typing effort. Oftentimes tab completion works the way it works in Linux terminals and other systems. So, I expect that it will also work with the Windows R interpreter. This immensely saves your typing effort once you know what is to be done. Okay, so what I showed you just a moment ago is how does one use R as a simple quick and dirty calculator. You don't need to do you don't need to learn much to be able to use that. Standard operators like exponentiation are here. So, 4 to the power 4 is 256 and so on. The Fortran like double star operator also works for exponentiation. One of the things about programming languages is that programming languages allow you to access memory locations by giving them names. So, for example, you could assign the value 5 to a variable called x. This peculiar operator here is one of the assignment operators in R. What this says is this operator explicit makes the direction of assignment explicit. The left hand side is a name, the left hand side is what a programming language would call a variable, and the right hand side is the value that is being assigned to the left hand side. That is how one reads this expression in R. So, when you type x left arrow 5, it will not print anything on the interpreter screen, but it will it will store the value 5 in a variable called x. You can see what you have created in the R workspace through the function called ls. Many of the functions in R are modeled after Unix or Linux commands. So, ls is an example of that. Ls shows that in the R workspace you have a variable called x. You could type x here on the interpreter command line, press enter. You will see the value of this variable, which is 5 in this case. You could reassign the value of, you could reassign some other value to x. You could assign a whole expression to x. What x will now contain is the value of this expression. So, programming languages give you this facility to assign values, associate values or associate data with a particular name, and then the name is something that you choose, which is easy for you to remember, and that way you get to keep track of things better. So, this is the purpose of assignment. Now, R also allows you the standard assignment through the equal to character. So, this will also work in the same fashion, more or less the same fashion. Okay, just as a curiosity, the right assignment also works, but the right assignment will also work, but not in this particular case, because on the right hand side you expect a variable here. You could do it this way, and x gets assigned the value of 5, and it works the same way. The basic data types that almost any programming language provides, these are the numerical variables like integers, real numbers, complex numbers, logical variables which take binary pair of values true or false, and character variables that store string or character data. These are all available in R. Let me not go into these things at any detail right now. Standard arithmetic operators and logical operators are more or less the same as in many other programming languages, and it is not very difficult to find out what these are. So, let me skip that part right now. Later on we will see examples of R scripts and programs which will use these things. So, it is not very difficult to pick these things up by reading programs also. basic language structures which are common to all programming languages, like conditionals, which means if statements. If a condition holds, then do something, or else do something else. This is there in R. For example, you can look up the help on conditionals through help page on if, or it lists the if, the two forms for the if condition. It also lists the loop structures available in R. So, the for loop, which is like in C, or the for and while loops as they are in C, they are very much have a similar syntax here in R, not exactly the same. Repeat until loops are also available, but the R repeat until is a little contrived, and all the programming machinery associated with these loops is also available in R. So, let me just mention this and leave it at that. Finally, finding help within R, we just talked about it. There is this whole help system. Let me also point out, if you do not exactly know which entity you want help on, you can search for help using some kind of fuzzy description. So, for example, if you want to find out which variables exist in the R workspace, suppose you search for list. This will give you a whole long list of things which are relevant to the search query, which I had what I had given was list. So, it gives you sometimes very long lists, like in this example, of things which may be relevant to the query at hand. So, sometimes this can be overwhelming. These days oftentimes it is just easier to ask Google. Somebody else would have faced the same problem, and you would find it much easier. But the point is, this kind of help system exists, and help search facility exists, and sometimes it can be quite useful. Outside of R, as I pointed out, the primary websites are the r-project.org website, and specifically the CRAN website. There is a large body of documentation about R, including tutorials available at the CRAN website. And apart from that, you also have a large body of literature in all kinds of forms, including books and web pages and so on and so forth, dedicated communities and blog pages and so on, which are available on the internet. So, this is where one finds information about R within R and outside of R. So, with this, let me conclude this particular session. And okay, let us begin with the next part of this introduction to R. As we said some time ago, R is an open source statistical computing environment which is rich in primitive operations which are required for statistical data modeling, data analysis. It is an open source thing, so there is a large community support. So, that is the advantage of using R. Let us talk about some of the most commonly used data types in R. These are what I would call container types. These are not like a single integer variable, but something that allows you to stack multiple things together. Let me go back to the R environment. I am at the interpreter is waiting for the next command or next expression to be typed. Let us talk about vectors. In mathematics, we talk about vectors we use vectors to represent points in a 3-dimensional space, or points in an n-dimensional space, or just to create ordered lists of objects. R vectors are similar, but not exactly the same. So, one way in which you can create a vector in R, I am just going to use generic names like x and y just for simplicity. One oftenly used kind of vector is a list of integers which are sequential from say 1 to 10, or from -1 to +10, for example. So, there is a crisp operator which is this colon. This will create a vector of values. The elements of this vector go from -1 to +10, and this is being assigned to variable called x. if I type x and print and press enter, it will print the contents of this vector x. So, you see the values which we intend to be contained in vector x. So, from -1 to +10. One standard thing one wants to know about a vector is how long is it. So, there is a function called length. So, length of x gives you the length of x, -1 to +10 is 12, right. You can also, connecting back to what we said some time ago, if you are not sure about what a particular function does, you can always go back to the help and see what it does. You can it gives this help page tells you what the help function does. The other thing that one often does with vectors, both in mathematics and in R, is to assign values to particular components or elements of the vector. This also requires one to access individual elements. In mathematics, we use the subscript notation oftentimes to indicate specific component of a vector or specific element of a vector. In R, we use square brackets and give an index. This is one of the ways in which one can access elements of a vector. So, first element of x is -1, second element is 0, fifth element is 3, 12th element is 10. If you go past this thing 13, I mean if you go past the length of the vector, it will throw something called NA. NA stands for not available in R. This represents something that is just not available. So, it is a special value in R. There is something peculiar that happens when you give negative indices. Negative indices basically are interpreted as omission. So, this peculiar expression in R stands for elements of x which or the sub vector of x, subset of x, which is obtained by deleting the first element. So, what you get is this thing, this is your original x, and x with -1 as the index gives you a vector which is without the first element, which happens to have the value -1. So, negative indexing is oftentimes very useful, and R has provided this facility. Another thing you can do with indices is, we created this vector, I mean we assigned this, we created this vector -1 colon 10, assigned it to x. Say in the same way you can create a vector which is 1 colon 5, which means vector with values 1, 2, 3, 4, 5. We can use another vector, another integer vector to subset a given vector. So, what this will pull out is the elements 1 through 5 of vector x. There are many other ways of accessing elements of a vector. So, for example, we did not talk about logical expressions, but for example, what you can do is, I am purposely putting in spaces, they do not matter here, I am putting in spaces for readability. Suppose you want to pull out all the values of x which are larger than 2, for example. So, what this thing does is, what you have put in as the subsetting expression is a logical expression which is x greater than 2. Okay, we'll just let's just go step by step. This is a logical comparison for numerical smallness or largeness. So, x greater than 2 gives you a logical vector with trues and falses. So, obviously, this is -1, this is 0, this is 1, this is 2. What we want is x greater than 2. So, rest of the elements are true here. We can subset this vector using this logical vector. The result of operation, the result of the expression, the value of the expression x greater than 2 is this particular vector here, and we can use that vector to subset vector x itself. What the way R vectors behave, this will only pull out those values where this condition is satisfied. So, this is what you get. So, you can access elements of a vector through logical expressions. You can also, interestingly, you can also associate names with x. So, for example, there is a standard variable in R that is called letters. I will just pull out the first 12 letters of this vector called letters and assign those as names to x. If you type x and press enter, you will see a slightly different display here. It prints values in x together with their names here, and once you do that, you can access elements of vector x using the names. So, eighth element of x is -1, lth element of x is plus 10, and so on and so forth. Okay. So, R allows you these nice things. These are oftentimes useful if you are specifically associating values with specific entities which are named, and then it becomes easier for you to remember pulling out a particular element and so on and so forth. So, R vectors behave this way. Operations on arithmetic operations on vectors behave more or less the same way as we expect them to be. So, x plus x gives you 2 times x, 2 star x gives you the same thing. An interesting situation occurs when you have got vectors of different lengths. So, first let us just create a vector which is of a different length than length of x. Length of x is 12 as we know it. Suppose we create a vector y which is x padded at the end by the vector 1 colon 5, 1 colon, okay, anything will do, 1 colon 4. Okay. You will see this peculiar letter C. This is a single letter name for a function. C stands for combine in R, and this is used so rampantly and oftentimes misused that it's I thought it would be better to show this to you. What this C does is to combine its arguments into a single vector. So, C takes x, pads the vector 1 colon 4 at the end and returns the value, and through this assignment this value is being assigned to variable called y. So, this is your original x, this is the vector 1 colon 4 as we expect it to be, and vector y looks like this thing. Names are carried over correctly. The x part of y carries over names, but the y part of the 1 colon 4 part of y, we haven't assigned any names to it. So, those names remain blank. You can check for length of y, again it is 16 as expected. You can access the 13th element of y, which is happens to be this one here, so on and so forth. So, everything that works for a vector also works for y. Now, the reason for creating this, let me just clear the screen, Control L works. This is my x, this is my y. The lengths are not same. One has length 12, the other one has length 16. Suppose as we saw, if I add x with x, it works as we expect it to work. If I multiply a vector with a scalar like 2 times x, x times 2 also will work the same way. This also works exactly the same way. You can take the second power of x, it will work exactly the same way as we expect it to be. Now, let us try what happens when we add x with x and y together. What happens is this -1 gets added to this +1, resulting into this 0 here. This 0 gets added to this 2 here, resulting in this 2. This 1 gets added to this 3, giving us 4, and this 2 gets added to this 4, giving us a 6. So, essentially what is happening is the shorter of the two vectors, which happens to be this x, is replicated once, and then to match the length of vector y. So, only the first 4 elements of y, first 4 elements of x are required to be padded at the end of x to match the length of y, and that is where you get 2 vectors of equal length, and then that is what results in this addition. So, this is something like, okay, I am just doing it once again. I am padding the first 4 elements of x at the end of x, and then now the resulting vector, this whole expression starting with a C, is my padded vector x. I am adding it to y, and what you get is exactly the result of operation x plus y here. So, these R vectors behave in a slightly non-intuitive way if you are used to mathematical vectors, but once you get used to it, they become intuitive. This behavior becomes intuitive and you can use it to your advantage. Oftentimes it makes your life easier as a programmer. Let me just mention couple of other container types in R. Just as you have a type container type to represent a mathematical vector, there is also a container type to represent a matrix here. Let me just show you one quick example and we will stop there. Again, help on matrix is available from by invoking help. I am not going into the details of that, just wanted to point out this thing. This is one way in which you can create a matrix. Okay. Suppose you want to create a matrix which is 3 by 3. You need to supply the vector of values that go in the matrix and then tell the size of the matrix, which is 3 rows 3 columns. What it gives you is this matrix. Now, this is read in the same way as we read matrices in a book, that is they are written in a row wise fashion, but you will notice that you had given this vector 1 colon 9, which is 1 2 3 4 5 6 7 8 9. What you will notice is that the sequence 1 2 3 has gone into the first column of this matrix, the sequence 4 5 6 has gone into the second column, and the sequence 7 8 9 has gone into the third column. Now, this is by design. This is how matrices are stored internally as one contiguous block of values as a vector, as if it was a vector, and the way this thing is interpreted by default is that this is considered as a matrix which is specified in a column wise fashion. There is a reason for doing this. This goes back to the Fortran convention of representing matrices in a column wise fashion. R has adopted that convention. C the C language stores matrices in a row wise fashion, that is a different convention. So, if you are moving in these two words, then you might have to worry about correctly interpreting your matrices, but if you stick to R or R and Fortran, then this column measure convention, as it is called, column measure representation of a matrix inside the memory, is common to R and Fortran. You will not have to worry about it. If you want the same data to be interpreted as given row wise, you need to specify another argument to this function called matrix. You will find help, the help page for matrix will explain you the details of this thing. What you get now with this additional argument here is a different matrix where the rows are 1 2 3 4 5 6 and 7 8 9. This is one thing I would like to point out about matrix and then stop there. More complex container types exist. One is called a data frame. This is like a matrix, but it allows you to have one column which is a logical vector, another column which is a numeric vector, third one which is a complex vector, and so on and so forth. So, it allows you to mix different elementary data types together in the form of different columns or different rows. A list is a far more liberal structure which allows you to store one element of a list can be a single number, another element could be a vector, third element could be a matrix, fourth element could be another list, and so on and so forth. So, list is a far more general basic container data type. What we have been seeing, okay, the last thing I would like to comment on is there is this we have been seeing many such expressions in the this session and the previous ones, where there is a name associated with the there is a name which is followed by parentheses. So, all such entities are what are called functions in R. Functions in R are similar to functions in C or in any other programming language. The purpose of a function is to encapsulate a particular computation or a sequence of operations or a particular algorithm which is used so ubiquitously that the code should be encapsulated in the form of a black box. These black boxes are called functions, and one can write simple functions. So, for example, suppose we are interested in the dot product of two vectors. Suppose the two vectors are x and y, and let us also assume that they are of the same length. We actually need to enforce this assumption, but one way to write this function is, let us assume that the users are educated and well meaning users, they will not try to break the function. So, let us assume that the lengths of x and y are the same, and x and y also happen to be numeric vectors, so that their multiplication is a well defined operation. The dot product of two vectors is multiply vectors x and y element wise. This is what is the R star operator when used for vectors. It will do an element wise multiplication of elements of x and y. We have assumed them to be of the same length. So, first element of x multiplies first element of y, second element with second, and so on and so forth. And then for the dot product, we need to take the sum of all these individual products. So, there is a function in R that is exactly called sum, which will do the trick, and there you go. This is a simple function that computes the dot product of two vectors. To use it, what you do is, suppose you want a dot product of vector, I will just take the dot product of the same vector with itself. This is, in mathematics, this would be the norm squared of this vector, which is a 5-dimensional vector with components 1 through 1, 2, 3, 4, 5. So, this gives you this number. So, this is exactly like multiplying the two vectors together, that gives you a vector, and then you take the sum, that gives you this number. So, so this is how one typically writes functions. If you are familiar with C, C requires the return statement. R also provides you with a return function to return the value of a function. Usually, it's a good idea to explicitly encapsulate whatever you wish, whatever you want your function to return, encapsulate it in the call to function return inside the body of your function, so that it is whatever is returned is made explicit in this coding, less chances of an error, so on and so forth. The effect is the same if you call this function. Now, okay, interestingly, earlier we had defined this function to be this thing without the return, a call to the return function. Now, we have used the same name for the variable, but then we have changed the value, which is the right hand side of the assignment. Functions are defined through assignments. Okay, functions are defined this way, but names are associated with functions through an assignment. So, what happened between this assignment here and this assignment here is that the left hand side, the value contained in the left hand side variable got rewritten, overwritten. So, the function dot now contains the latest definition. This is how all reassignments work. Anyway, the result will be the same, the result of the computation will be the same, it gives you the same thing. So, with this, let me stop this really quick and dirty introduction to R. I hope you have got enough to get going into the R domain. Interestingly, when I was introduced to R, the only two things that were told to me was this function called C, which we have used earlier. This is the help page for C. That was the only thing that was told to me, and the other thing that was told to me was this function called help, which gives you help on. So, for example, you can take help on help using this expression. This was the only thing that was told to me, but then it turned out that if you know any other programming language, many of the things work about the same way. Whenever you need to worry about details of how exactly a particular function works or how a particular operator works and so on and so forth. There is large amount of documentation and literature available. So, I hope that this introduction will be quite enough to get you going. Later on in the next two sessions, we will see examples of R scripts, R programs saved to a file, and that is where we will get hands dirty with R. So, thank you.